Okay, welcome back. So now we want to consider this for the case of logistic regression. How do we build a likelihood function in this case? Well, in this case, remember the data that we started with, the CHD age data, we had a 20-year-old who did not have CHD, then a 23-year-old who did not have CHD, and then a 24 and a 25-year-old who did not have CHD. Then we had a 25-year-old who did have CHD, and then we had lots of observations, but we have 100 altogether, and finally a 69-year-old who did have CHD. So how are we going to write down the likelihood function for this? So we can start, and we can say, okay, here's the likelihood function. Likelihood function is, okay, what's the probability that a 20-year-old does not have CHD? And remember the model is, that probability is 1 over 1 plus e to the beta naught plus beta 1 times 20. And so that, what I've written down is the logistic regression, the logistic probability that a 20-year-old does not have CHD. All right, now what's the probability that a 23-year-old does not have CHD? So that's 1 over 1 plus e to the beta naught plus beta 1 times 23. And then a 24-year-old does not have CHD. 1 over 1 plus e to the beta naught plus beta 1 times 24. And then a 25-year-old does not have CHD. 1 over 1 plus e to the beta naught plus beta 1 times 25. And then the probability that a 25-year-old does have CHD, which is e to the beta naught plus beta 1 times 25 over 1 plus e to the beta naught plus beta 1 times 25. All right? And now this continues, another 96 times or 95 times. And finally, you come to the last person in the data set, who's a 69-year-old who does have CHD. So that's just e to the beta naught plus beta 1 times 69 over 1 plus e to the beta naught plus beta 1 times 69. That's it. I've just written down the likelihood function. Okay? And again, the same rules that I talked about before apply here. I can write down this function. I can take the log of the function. That'll be the log likelihood. Now, the idea of taking derivatives of that and then solving the derivatives is not going to work, because it's not simply a linear function, and we're not going to be able to solve for beta naught and beta 1 that way. Instead, we're going to rely on computer software that's going to use Newton-Raphson estimation to iterate into a solution. And in fact, it's very exciting because the program will start out with its first guess, and then step by step it will iterate into a solution. Now, depending on how slow your computer is, that will be an indicator of how exciting this process gets. Because if you're using a very old, very slow computer and a big data set, it'll do the first iteration, then sit for a while it thinks and calculates, and then it'll come up with the second iteration. And this process all takes a lot of time. Okay, if you have a fast computer, it's not very exciting at all, because you push the button and all of the iterations come out, and finally you get the final log likelihood. That is the value that maximizes the log likelihood of this expression. So that's so it's choosing the values of beta that maximize the log likelihood. Well, and of course, maximize the likelihood. So that's what maximum likelihood estimation is all about, and that's what is going to be done in these computer packages when it maximizes the likelihood function. So I'll just review again with you about maximum likelihood. So the method of maximum likelihood yields values for the unknown parameters that maximize the probability of obtaining the observed set of data. And with this method, as I said, we first construct the likelihood function, and that gives us the probability or the likelihood of the data for some arbitrary values of the parameters. And then we determine specific values for the parameters that maximize the likelihood function. So here we have, let's set y equals our outcome variable. That's 0 or 1, presence or absence of the outcome. Pi of x is, again, the probability that y is equal to 1 given x, which is simply e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. So again, that's the probability that y is equal to 1 given x. So it follows, again, that 1 minus pi of x is just 1 over 1 plus e to the beta naught plus beta 1x. That's the probability that y is 0 given x. So for an arbitrary value of beta, that is either beta naught or beta 1, the probability that y equals 1 given x is pi of x. The probability that y is 0 given x is 1 minus pi of x. So for those people who have the outcome, that's for those people with y equal 1, the contribution to the likelihood function for them is pi of x. And for those people who don't have the outcome, that is people with y equals 0, their contribution to the likelihood is 1 minus pi of x. Now, a convenient way to express the contribution to the likelihood function for the data xy is through this term, this Greek symbol xi. Okay, and xi of x is pi of x to the y-ith power times 1 minus pi of x to the 1 minus y-ith power. Now, this is an interesting, very interesting function. So, for example, if the individual has y equal 1, that is, the individual has CHD, then y is equal to 1. 1 minus 1 is 0, so you have pi of x to the first power, 1 minus pi of x to the 1 minus 1 or 0th power, so that's just 1. So if the individual has y equal 1, then the contribution to the likelihood is pi of x. If the individual has y equals 0, then this becomes this to the 0th power, this is 1, so this is their contribution to the likelihood function is 1 minus pi of x. So it's a beautiful function, this xi, because all you have to do is to write down the likelihood function. You simply take the product from I equals 1 to n of the xi's of xi's. Okay? Now, this symbol, this Greek symbol, this capital pi, is the product of observations from 1 to n. Unlike the Greek sigma, which is the sum of observations from 1 to n, this is the product. So here I'm taking the product of these xi's over all of the data points. Again, each time, if y is equal to 1, you get the contribution pi of x, and if y is equal to 0, you get the contribution 1 minus pi of x. So in maximum likelihood, we use as our estimate of the betas the value that maximizes the likelihood function. However, as I said before, it's easier mathematically to maximize the log of the likelihood function, and that's called the log likelihood, denoted capital L of beta. And so capital L of beta, which is the log of the likelihood, now again, if we go back, notice that what we're going to do is we're going to take the product, so the product becomes a sum when you take the log, and then you have an exponent here, so it's going to be yi times the log of pi xi plus, not product, plus 1 minus yi times the log of 1 minus pi xi. And so that's what we have here. This is the log likelihood function. We no longer have products, we have sums, we no longer have exponents, they've been coming down. So this should be an easier expression to deal with. And so to find the maximum likelihood estimate of the betas, we would differentiate the log likelihood first with respect to beta naught, set it equal to 0, then with respect to beta 1, set it equal to 0, and now you have these likelihood equations, you have unknowns. The problem is that this pi of x, it looks innocent enough, but it has e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. So it's not going to be possible to solve these equations simultaneously for beta naught and beta 1. So remember that in regression, in linear regression analysis, the likelihood equations are obtained by differentiating the sum of square deviations function with respect first to beta naught, then beta 1. These equations are linear in the unknown parameters. They're linear in beta naught and beta 1, and so it's easy to solve for them. But for logistic regression, the likelihood equations are not linear in beta naught and beta 1, and they require these special methods. And as I said, these methods have been, they're iterative. They have been programmed into available logistic regression software, this Newton-Raphson method, and so it's actually very easy for us to compute the maximum likelihood estimates because we have the available software to do it. One point before we begin to look at the data again is we let beta hat, now this underbar just indicates that we have a vector of beta, so we're estimating more than one beta coefficient simultaneously, so we're estimating beta naught and beta 1 at the same time. So we're going to let beta hat denote the maximum likelihood estimate of beta, and pi hat x denotes the maximum likelihood estimate of pi x. So this is our estimate of the probability that y is equal to 1 given x. Okay? And just one note is that if you sum up the y's, now remember y's are all zeros and ones, so if you sum up those zeros and ones over all of the subjects, you get the total number of people with the outcome variable. Similarly, if you sum up the estimated probabilities from 1 to n, the sum of the probabilities is also the total number of people with y equals 1. Okay? So that's something to keep in mind, that the sum of the probabilities is equal to the sum of the y's. So this is a good place to have a break. So let's do that, and then we'll come back in whenever you're ready, and we'll continue with our study of logistic regression.